Hi, and welcome back to Codex. Today we have Professor Daniel Freeman from St. Louis University, or as the cool kids call it, Slussel. Professor Freeman is an expert in Banach spaces, frame theory, and phase retrieval. Today he'll tell us about recovering vectors from saturated measurements. Take it away, Dan.
Well, thank you for the introduction, John. So for those who don't know, Slussel stands for St. Louis University in St. Louis. So I'm going to talk about some work with my collaborators, Dad, Dorsa, Brody, and Lova, who are all at St. Louis University, and it's been really fun talking to them and working with them on this project. Okay, so I'm going to start just with a little bit of motivation in discussing continuous frames. And so we have a Hilbert space and a measurable collection of vectors in the Hilbert space. And I'm going to kind of give the motivation for the definition of a continuous frame. And so I'm kind of defining the object after using it. And so the idea is I want a operator that takes my Hilbert space into capital L2, where theta x is going to be the function where its value at point t is just going to be the inner product with the frame vector xt. And so the idea is here, just any old vector in my Hilbert space. I apply this analysis operator. Now I have a useful, hopefully, representation of my vector in L2. And so you could think of theta as being maybe like the short time Fourier transform or wavelet transform, something like that. So one of the things that's really important is when I map this vector x into L2, I do some analysis here. I want to be able to go back to my Hilbert space, and so I want an inverse operator for my transform. And this inverse operator is going to be defined in this way. And so this is a very general setup that comes in a lot of different situations. And essentially the conditions that we need for this to be possible is for there to be uniform constants, so that first, this operator is bounded in norm, and so that the range of h is inside of L2, theta has to be bounded. And so that would be there exists a constant b, so that this inequality is satisfied. And then we also want to be able to recover our vector using a bounded operator. And in order to do that, we need a constant a such that this lower inequality is satisfied. And so this is just called the frame inequality. And essentially having a frame says that this kind of setup is possible. And if I wanted to express it in terms of the exact L2 norm, this would be the frame inequality. And so if this holds for some constants a and b, then we say that this collection of vectors is a continuous frame. If I have instead a discrete set with counting measure, then this integral just becomes a sum, and it looks like the normal inequality for a discrete frame. Okay. So with this idea in mind, let's think about phase retrieval and saturation recovery. And so the idea for phase retrieval, one of the ways I like to think about it is I have a continuous frame. My continuous frame gives me a bunch of frame coefficients, which are measurements of some vector, but sometimes I can't obtain the full frame coefficients. I can only obtain the absolute value of the frame coefficients. And so in this situation, in normal linear frame theory, my analysis operator would give me this function, and then I could go back by inverting it. But with phase retrieval, we're in some situation where I can only obtain the magnitude of my frame coefficients. And so this comes up a lot in electron microscopy, coherent diffraction imaging, lots of fun physics problems are in a situation where you take a bunch of measurements, but you can only obtain the magnitude of those measurements. And so the goal of phase retrieval is I'm looking at some absolute value of a function. How do I go back and recover the vector that I'm measuring? Okay. And then now let's think about this in terms of a totally different problem, saturation recovery or declipping. So it's a similar situation where there's some vector that I'm interested in. I apply some transform, but now the way that I'm obtaining these measurements, I'm using sensors that have some fixed range. And so if I have some measurements that are small, I can detect these measurements very well. But any measurement that's outside of the range of my sensor, it just gets clipped and outputs the maximum of lambda when it's positive, and I'll output the minimum of negative lambda when it's negative. So this comes up a ton in audio signals and electrical engineering, things like that. And so the goal of saturation recovery declipping is I'm looking at some signal like this. I want to know, how do I figure out what is the vector that is giving me this clipped signal? And so essentially we could think about for phase retrieval, we want a recovery map. And so if I'm looking at any signals of any measurements of this form, I want to figure out what's the vector that gave that. Same thing for declipping or saturation recovery. We want a recovery map. And here we have these two nonlinear transforms that we considered in a paper by Daniel Hayter, Martin Eller, and Peter Balish. They considered the ReLU activation function from which is used in machine learning. And in this paper and a bunch of other papers, they looked at the mod function and considered this problem in that context, where with saturation recovery, I clip the signal, but with the mod function, what'll happen is when my signal goes up to this lambda, it'll jump back down to here. And so what'll happen is instead of getting this clipped part, this mod function is going to recover what do the peaks look like. And essentially it's the idea of this paper is you want to do saturation recovery, but you change the hardware so that instead of the hardware clipping the function, it folds it back on itself a bunch of times. And so it's a different solution for trying to solve the same problem. Okay, so this is kind of the idea with continuous frame. And in a lot of applications, you can take advantage of if this is a continuous function, and I want to recover from something like this, you could look at things like, oh, okay, well, if it looks like I'm going to be crossing the x-axis here, so probably a good guess is to go like this. And then over here, with this clipped part, it's like, looks like I'm going up to a peak, so probably my function looks like this. Here's another trough, so it looks like that. And so using the continuity can be really helpful in solving this problems. But one of the difficulties is a lot of times in applications, you don't want to take a huge number of measurements, and so you get a continuous function out. You want to do discrete measurements. And so you want to do some sampling of the transform. And so if I sample that transform at some discrete points, and I want to do phase retrieval, there's no way to see where I'm crossing the x-axis. And so recovering the vector from these discrete phaseless samples is going to be way harder. And there's a lot of interesting work on this. Like Rima Alifari and Philip Gross and their collaborators have a bunch of papers considering, how can you sample these continuous transforms and do phase retrieval. And then in the setting for lambda saturation recovery, it's not clear, how would I go from here back to there? Because I don't have a continuous function anymore where I can just identify the peaks that got chopped off. So it's a much harder problem. Okay. So one of the goals of my talk is to kind of discuss some of the cool work that people have done considering phase retrieval from a frame theory point of view, and discuss, well, what happens if I ask those same questions about phase retrieval and change, instead of this absolute value function, change it to the saturation function? What do those questions about phase retrieval look like, and what happens in that situation? Okay, so let's just formulate the general problem for phase retrieval. So I have a frame with some analysis operator. I'm going to define an equivalence relation on my Hilbert space as saying if x is equal to a unimodular scalar times y, then x and y are equivalent. And we say that the frame does phase retrieval if, when I look at the absolute value of the analysis operator, when applied to the quotient space, when I mod out by this equivalence relation, that this is 1-to-1. So that is two vectors are equivalent if and only if the absolute value of their frame coefficients are all the same. And so what would be natural question for saturation recovery? So we have a frame. We consider this saturation operator that in between negative lambda and lambda, it just is the identity. And if it measures anything above lambda, it outputs the max. If it measures anything below negative lambda, it just outputs negative lambda. And I'm specifically going to restrict myself to the unit ball now, because if you take a vector with huge norm, everything's going to get saturated and you can't know anything. And so let's just restrict to the unit ball. And we say that a frame does lambda saturation recovery on the unit ball if this composition of the analysis operator with this saturation operator is 1-to-1. And so that is two vectors are equal if and only if phi lambda of their frame coefficients are equal. So one of the simplest questions you can ask is, how do you know if a frame does phase retrieval? And in the case of Rn, they proved that a frame does phase retrieval if and only if it has the complement property. And so that is, doing phase retrieval is equivalent to whenever you partition your frame into two sets. And so if I partition it into the frame vectors whose coordinates are in J naught and the frame vectors whose coordinates are not in J naught, then at least one of those is a frame. And so that's what they call the complement property. One thing to point out is for complex Hilbert spaces, the complement property is necessary for phase retrieval, but it's not equivalent. So here's an example. If you pick a bunch of frame vectors where each coordinate of your frame vectors has modulus 1, and so I'm doing this in C2, no matter how many frame vectors you pick, it's not going to do phase retrieval because, if I take the vector, which is 1 in the first coordinate, and look at its inner product with one of these frame vectors and then do its absolute value, well, this has modulus 1, so this is just going to be 1. And likewise, if I look at the vector, which is 1 in the second coordinate and 0 in the first coordinate, it's going to be the same. And so you have these two vectors that are orthogonal, totally different from each other, but all of their frame coordinates are 1. Okay. So natural question, how can we know if a frame does lambda saturation recovery? And so we proved that if you take a frame for Rn, and then for each vector in the unit ball, these are going to be the coordinates where saturation does not occur. And so the absolute value of the frame coefficients are less than or equal to lambda. And then the frame does lambda saturation recovery on the ball if and only if for every vector x in the ball, if we look at the frame vectors corresponding to the unsaturated coordinates, that forms a frame. So kind of to compare with phase retrieval, so doing phase retrieval says if I partition my frame into 2 sets, at least one is a frame. Doing lambda saturation recovery says whenever I partition into specifically the saturated coordinates and the unsaturated coordinates, I have that the unsaturated coordinates form a frame. And in their paper, Hader, Eller, and Belash, they proved the analogous theorem where if, instead of using the saturation function, you use the ReLU function. Okay.
Hey, Dan, I got a question for you.
Yes.
What is H?
Oh. Good question. Rn. Sometimes I wrote H as Hilbert space, and sometimes I had H. Yeah, so yeah, H is just Rn. Sorry. Okay. Hopefully that's all of my typos. Okay. So this characterizes when you can do saturation recovery. So one thing is if you take a huge frame with huge number of vectors, yeah, it'll do saturation recovery, but we want to be efficient and we want to know exactly how many vectors are needed. And so for the case of phase retrieval, if you take 2n minus 1 vectors in Rn, then unless you do something really stupid, it's going to do phase retrieval. So almost every frame of 2n minus 1 vectors does phase retrieval. If you take any collection of 2n minus 1 vectors and divide it into 2 pieces, one of those pieces is going to have at least n. And as long as those n vectors span, it's going to be a frame and so almost every frame of 2n minus 1 vectors does phase retrieval. And if you don't have that amount, then you can't do phase retrieval because it wouldn't have the complement property. You can divide it into 2 sets with 2n minus 1 vectors. And for complex Hilbert spaces, almost every frame of 4n minus 4 vectors does phase retrieval. But it turns out that you can actually do phase retrieval in complex sometimes with less vectors. And so this is really interesting that this 4n minus 4 vectors, if your dimension is 2 to the k minus 1, then that's necessary for phase retrieval. But there are counterexamples, which is pretty cool. Okay, so natural question. How many vectors do I need to do lambda saturation recovery? And I told Dustin that I was done with those typos, but so for the unit ball in Rn, how many vectors do I need? So one of the things is that how many vectors you need depends on your saturation level. If things get saturated at very small values of lambda, you're going to need more vectors. And so given some dimension n and some saturation level lambda, you could ask what's the smallest number of vectors I need. So there exists a frame of unit vectors, which does lambda saturation on the unit ball. And you can also instead fix a number of vectors in a dimension. And so I want to build a frame of m vectors. What's the smallest lambda so that I can construct a frame of m vectors, which does lambda saturation recovery? And so I think these are really interesting questions that I don't think people have asked before. I'm a little scared right now because I'm not 100% sure, but I don't think people have looked at this. So let's think about how can we reformulate this? So how do I find the smallest lambda so there exists a frame of m unit vectors, which is lambda saturation recovery? So our characterization of lambda saturation recovery tells us that these two problems are equivalent. What is the smallest lambda greater than 0 so that there exists a frame of m unit vectors so that if you ever look at the unsaturated coordinates, that this is a frame. And so let's look at two cases. So the first case is m equals n. So this isn't very interesting. If I take any basis of unit vectors for Rn, if there's any saturation recovery at all, I'm sorry, if there's any saturation, then it's not going to work. So every basis of unit vectors does one saturation recovery, and if lambda is ever smaller than 1, you can't do saturation recovery. So let's look at the next interesting case. So here, if you ask for a frame of n plus 1 unit vectors, then an equiangular frame of n plus 1 unit vectors, it does saturation recovery for this value of lambda. And this is the smallest value of lambda that any frame of n plus 1 unit vectors will do saturation recovery on unit ball. So let's look at how this works out. So here's the Mercedes-Benz frame. And so it's a equiangular frame of n plus 1 vectors in R2. Because we're looking at the absolute value of inner products, so the vector v1 and the vector negative v1 are the same to us. So let's this will be negative v3. And then this will be negative v2. And then here I have negative v1. And I want to know what's the worst case scenario for saturation recovery? When can it fail? And so we want to consider a vector in the unit ball such that where's the exact point where saturation will happen. And if I saturate any further, the unsaturated coordinates won't be a frame. And so that'll happen at these points halfway between the frame vectors. because at this point, its inner product with V1 is going to be the same as its inner product, or the absolute value of its inner product with V3. And so let's say this vector is X. And so if X inner product V1 is lambda equals, I'll call it lambda sub C, which is the critical value. Then if I pick any saturation level below this, then I won't be able to recover this vector X. So if I take some lambda which is smaller than this, then the collection of unsaturated coordinates is just going to be V2. Oops. And so the unsaturated coordinates are not a frame. So essentially, in order to find the lambda where you get the smallest lambda where you get saturation recovery, you would look at the vector halfway between the frame vectors and then its inner product with these two frame vectors. That's going to be the lambda. Okay. Okay, so now I'm going to do an aside to sphere packing. Okay. So the idea is I take a collection of points in a metric space, and I say this is an epsilon sphere packing if I look at the balls of radius epsilon about these points, that they're all disjoint. So that's what I'm calling a packing. Okay. And now I'm going to generalize this, say that a collection of balls is a k-fold multi-packing if I can now allow these balls to overlap, but at any point in my metric space, it's in at most k of the balls. And so normally when people look at packing problems, they want a bunch of disjoint balls, but we're going to talk about multi-packings, and now my balls can overlap. And so I can add more points into this packing. And so let's say do something like this. So I've added some points now, and here I have 2 overlap, here 2 overlap, 2 overlap, 2 overlap, but I never have 3 of them overlap. And so this is a two-fold multi-packing. And so note that a packing is just a one-fold multi-packing. Sphere packing comes up in a ton of important situations. One example is in error correcting codes. If you transmit a code and there's some small amount of error in it, if the code is part of a packing, and you receive something instead which is different from what you're trying to send, you can still figure out what is the exact signal. And multi-packings correspond to what they call error correcting codes for list decoding. And so in this situation, it's okay to, if you don't recover exactly the code you're trying to send, but you have a list of things that you're treating as equivalent to it. Okay. So let's look at specifically packings in projective space. So n-1 dimensional projective space, it's the set of lines through the origin in Rn. And so if I have two lines through the origin, say this is L1, this is L2, the distance between those two lines in projective space is just going to be the smallest angle between them. And for notation, I'm going to write if x is any vector that's non-zero, this will be the span of that vector. And so it'll be that line in projective space containing that vector. And note that if you have two unit vectors, then the distance between their span is given exactly as our cosine of the absolute value of the inner product. So this is a massive problem to determine what are best packings in projective space and how do you construct them? If you have some packing in projective space, how do you know it's optimal? So I feel like I'm preaching to the choir here because I know, the organizers of the seminar love this stuff. So yeah. One natural obstruction is the Welch bound, that if you have a collection of unit vectors, then the biggest magnitude of the inner product between two of them is at least this value. And so that would be, if you did, that directly corresponds to the distance between their spans in projective space. And it's really cool that if you achieve equality in the Welch bound, that's exactly when your unit vectors form an equiangular tight frame, which are very desirable in frame theory. And so this is just one example where there's a very strong correlation between packings in projective spaces and constructing really good frames. Okay, so I went on this aside. Talking about packings in projective space, what do multi-packings in projective space correspond to? Let's consider a frame being full spark as meaning every subset of at least n vectors spans Rn. And so most frames are full spark. So our characterization of lambda saturation recovery, it pretty much immediately gives that if you have a full spark frame of unit vectors and you pick any saturation level lambda, then this frame does lambda saturation recovery on the unit ball if and only if we have an m-n fold multi-packing in projective space, where the radius is inverse cosine of lambda. So this is really cool that says, if I want to understand what are good frames for lambda saturation recovery, how do I construct frames for lambda saturation recovery? That corresponds exactly to multi-packings in projective space. So let's give a really short proof of this. So a frame does lambda saturation recovery on the unit ball. That's equivalent to the unsaturated coordinates form a frame for every vector in the sphere. And so the unsaturated coordinates form a frame means that because it's full spark, And so this line is because my frame is full spark, we have that a collection of vectors is a frame of Rn if and only if there's at least n of them. Okay, so being this, the unsaturated coordinates, there's at least n of them. Well, that's equivalent to, for the saturated coordinates, there's at most m minus n. And so that means the inner product between x and xj in magnitude has to be bigger than lambda. And now if the inner product between two vectors is bigger than lambda, the distance in projective space between their span is smaller than arc cosine of lambda. And this is exactly the condition that we have an m minus n fold multi-packing in projective space. So it's pretty much just follows immediately. And so tons of people are really interested in these packing problems in projective space. They're super hard, very interesting, lots of open questions. Much less people, there's much less work have been done on these multi-packings. And so one of the things that I think would be cool is if this gives maybe some motivation to look at this. And so I think there's very little known. Hopefully I didn't offend anybody saying that maybe prove something about multi-packings. But I think there's a lot of interesting possibilities for considering, given fixed sum k, what's the least epsilon, so you can find a multi-packing of a k-fold multi-packing of n vectors in projective space. And then how do you build such a packing? I don't have any answers for that. I think it's super hard, super interesting. Okay. Let's talk about stability of recovery real quick. So I have a frame with an analysis operator. For phase retrieval, I have, suppose it does phase retrieval, that means that if I look at the absolute value of the frame coefficients, then that's invertible. And so doing phase retrieval says you can invert an operator. Doing C-stable phase retrieval means that this inverse function is C Lipschitz. And so the idea is when you actually do some phase retrieval in applications, you care about resilience to error, you care about stability. And so being C-stable says that your recovery map is C Lipschitz. Then we'll say the same thing for saturation recovery. If I have a recovery map for lambda saturation recovery, I'll say it's C-stable, meaning that the recovery map is C Lipschitz. Okay. Turns out that in finite dimensions, if you have a frame which does phase retrieval, it does stable phase retrieval for some constant C. What about for saturation recovery? So let's take a finite frame in Rn. Lambda C is going to be the infimum of all lambda so that lambda saturation recovery is possible. Then what we have is that it does, at this infimum, it's actually a minimum. And so the xj does saturation recovery at this critical saturation level. And also, if you take any lambda bigger than it, for any lambda bigger than this critical level, our frame does stable lambda saturation recovery. And so if you give yourself a little bit of room, then you get stability. And I don't know what happens at this critical level. for a long time, I was 100% convinced that if you do lambda C saturation recovery, then it's stable. Just kind of the feeling that the unit ball's compact in finite dimensions. And so if you have a map that's continuous and one-to-one, should be stable. But now I'm not sure. I was 99% convinced, but now I'm not sure. I think it's really interesting. So now I want to talk a little bit about, and explain why I'm unsure. So if you have a frame, then a collection of vectors yj is called an epsilon perturbation if we have the difference, the sum of the difference squared between the frame vectors for xj and the vectors for yj is less than epsilon. And so it's a classical theorem in frame theory that if your epsilon is less than the lower frame bound, every epsilon perturbation of a frame is also going to be a frame. And we have a result that says if you have a frame which does C stable phase retrieval and epsilon is smaller than this value, then every epsilon perturbation of your frame is going to do stable phase retrieval with this value. And so if you know the stability of phase retrieval for a frame and you perturb it a very small amount, you can calculate the stability of phase retrieval for that perturbed frame. And so with saturation recovery, however, if you look at the critical saturation value for the frame, if you take any lambda bigger than it and just perturb your frame a teeny amount, it's still going to do lambda saturation recovery. But if you're trying to do saturation recovery at this critical value, you're not able to perturb your frame and still do saturation recovery. So here's a really simple reason. I take my frame, I perturb it by just making all the frame vectors slightly bigger. And so if I do that, things get saturated faster. But because this is the critical saturation level, it's not going to be possible to do saturation recovery with this teeny perturbed frame. And so this kind of gives me a little feeling that, well, maybe we don't get stability for saturation recovery at the critical level just because there's no room to wiggle anything. There's no wiggle room. Okay. So very last thing I want to talk about is actually how do you implement saturation recovery? So I have a frame with some analysis operator, and suppose that I've obtained some measurements. And so I have some sensors that have an bounded effective range, and this is what I've measured. How do I recover this vector x? So this would be I want to solve this problem then. So to find x, that's equivalent to finding a vector where all of these are satisfied, so that if in the range where we don't have saturation, the frame coefficients for y are exactly my measurements. And when I do have saturation, y is saturated positively where x is saturated positively, and y is saturated negatively where x is saturated negatively. So this is considered in these papers where they're doing compressed sensing with saturation. And they proved that essentially one of the very good ways to do compressed sensing, if you also have saturation, then you can do compressed sensing and saturation recovery at the same time by solving a linear programming problem where we want to do a L1 minimization. And so this paper is somewhat motivation for us in the sense that we're really interested in the case of using a frame. And so we're not just looking at sparse vectors, but one thing that you could do is make k equal to the dimension and sparsity goes away. And so then if you have some algorithm that works for compressed sensing, then it'll also work for the case of vector recovery using a frame. And so that kind of gives like a benchmark that if we're going to give an algorithm for lambda saturation recovery, it better at least beat that. Okay. So let's discuss the frame algorithm with the case where you have no saturation. So we have a frame with some analysis operator, and I look at the frame coefficients. The frame algorithm gives an efficient method for finding the vector x with those frame coefficients. So this is very well studied, and the algorithm is constructed by building a sequence. Sequence starts at 0, and then it iteratively makes a better approximation for the vector x. So if I built yk, then the next vector in my sequence is defined in this way. And so essentially what this is doing is I start with yk, and then I want to move so that the frame coefficients for my new vector move towards the frame's coefficients for x. And so in each single one-dimensional subspace, I think about I want to move yk towards x. And so I add some linear combination of these. And the classical inequality says that I haven't said what alpha is. Okay. Alpha is some coefficient between between 0 and 2 over the upper frame bound. Okay, and so the idea is that this algorithm actually converges exponentially fast. So the difference between the k+1 term in my approximation and the kth term, it decreases by some constant factor. And you can see that alpha can be anything. The best choice for alpha comes at 2 over a plus b, and in which case this constant is b minus a over b plus a. And so the frame algorithm gives a very efficient, computationally efficient way of finding the vector x so that, or approximating the vector x from the frame coefficients. Notice in particular, if you have a parsable frame or a tight frame, the frame algorithm will give the exact value of x in one step. If it's not a tight frame, then it probably won't terminate, but it'll approximate it very quickly. So what we did was look at this frame algorithm and think, what happens if I add in saturation? I want to kind of try to do a similar algorithm to what works with the frame algorithm. So we're in a situation where I have a bunch of measurements of this form. And so I have phi lambda of the frame coefficients. I want to approximate the vector which gave us these measurements. And I'm going to label these as the unsaturated frame coordinates. And then we can look at the positively saturated coordinates and the negatively saturated coordinates. And so now we can pick some weights and try to do the frame algorithm. So one thing that we can do is if I forget about saturation, if I forget about the saturated coordinates and just look at this, this is just the normal frame algorithm on the unsaturated coordinates. So what I'm doing is, in order to build our next approximation, I do the usual frame algorithm just considering the unsaturated coordinates. And then I add in some terms where I'm trying to get consistency with the saturation values for X. And so on these coordinates, I have X is positively saturated. This would be Y is not positively saturated. I'm trying to move Y towards this positive value lambda. And then in this case, I have X is negatively saturated, Y is not negatively saturated. I want to move the frame coefficient for Y towards negative lambda. So I feel like this is a pretty natural thing to do. But of course, there's a very obvious question. If this is a frame, I can do the frame algorithm just using the unsaturated coordinates. I can forget totally about this and it'll work. And yeah, you could totally discard the saturated coordinates and recover your vector. So then the natural question is this, can you do better by looking at the saturated coordinates? So with our frame algorithm, we can choose any coefficients we want. I'm supposing I start with a frame with frame bounds A and B, and I'm using the best coefficients for the frame algorithm for the frame I start with. So it's a natural coefficients to pick. This is the best you can do for the starting frame. If I do my lambda saturated frame algorithm with those coefficients, then we have the following. So if I look at only the unsaturated coordinates and suppose it has some lower frame bound A prime, and then kind of awful looking, but this would be all of the coordinates that get used in the unsaturated frame bound. If by putting in those other additional coordinates, if I can increase my frame bound any amount, then what I have is that using the unsaturated frame algorithm, using the lambda saturated frame algorithm, it beats the normal frame algorithm using just these vectors. And so the normal frame algorithm, this would be the constant you would get for trying to recover X. Here with the unsaturated frame algorithm, I beat it some amount. And so the amount that I beat it by, it depends on the stage of the iteration. At the start of the algorithm, when I'm building the sequence to start, these epsilon k's in practice tend to be bigger, but then they'll converge to 0. So after a certain point, you really only need to worry about the unsaturated coordinates. And so just a couple examples. We did a frame of 30 unit vectors in R10, picked lambda saturation level to be 0.4. Here we did the normal frame algorithm on the unsaturated coordinates. So in black, this is just the normal frame algorithm using only unsaturated coordinates. Here, this is doing the lambda saturated frame algorithm. And so you can see it outperforms it, but both of them at this saturation level do pretty well. If we now have saturation at 0.25, you get a very dramatic improvement by using the saturated coordinates. And so in this situation, we have 15 saturated coordinates out of a total of 30 vectors. So half the coordinates are saturated, and our lambda saturated frame algorithm performs much faster. And I will stop here.
All right. Thanks so much, Dan. So I want to encourage everybody to smash that reaction button to thank Dan for a great talk. And if there are any questions,